Let's talk about matrix multiplication. Let A equal 1, 2, 3, 4, and B equal 5, 6, 7, 8. Find AB. Here's how we calculate AB. It's basically multiplying this row and this column. It's 1 times 5 plus 2 times 7. Okay, so first row, first column, it's going to be in the first row and first column of AB. First row and second column ends up in the first row and second column of AB. So it's 1 times 6 plus 2 times 8. Then we've got 3 times 5 plus 4 times 7, and 3 times 6 plus 4 times 8. In other words, 19, 22, 43, and 50. Okay, how about A, 1, 2, 3, 4, B, 5, 6, 7, 8. Find BA. BA, oh my goodness, it's kind of tough. So you need to, I'm going to write B over here. It's just easier to do this. So you write B. It's 5, 6, 7, 8. Okay, let's do this. So it's going to be this row times this column. So it's 5 times 1 plus 6 times 3, in other words, 23. And then 5 times 2 plus 6 times 4, in other words, 34. And similarly, 7 times 1 plus 8 times 3, 31. And 7 times 2 plus 8 times 4, in other words, 46. So what I'd like you to notice is that AB does not equal BA in this example, because AB was 19, 22, 43, 50, and that's not what BA is. Matrix multiplication is not necessarily commutative. Might be, but not necessarily. Okay, let A equal 1, 2, 4, 2, 6, 0, and B equal, oh my goodness, that matrix. Find AB. Okay, hope you got a cup of coffee on your side, because this is going to take a while. So AB, again, is going to be this row, first row times the first column. So we end up with 1 times 4 plus 2 times 0 plus 4 times 2. Okay, and then we've got this row times this column, blah, 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 blah. So that's going to be 1 times 1 plus 2 times negative 1 plus 4 times 7. And you just keep going. This row times this column, and then this row times the fourth column. And then we've got this row times the first column. Again, second row, first column, ends up being in the second row, first column of AB. So we've got 2 times 4 plus 6 times 0 plus 0 times 2. Okay, we simplify all, and you just keep going. This row times this column, this row times the third column, this row times the fourth column. And this is what we end up with. 12, 27, 30, 13, 8, negative 4, 26, 12. Let A equal 1, 2, 4, and 2, 6, 0. Okay, B equals the same matrix. Find BA. Oh, you can't. It's undefined, because how would that work? You just can't do that, because it would be this row times this column. Oh yeah, you can't do that. That's not going to work out. If A is an N by P matrix and B is a P by N matrix, then AB is an M by N matrix. So notice, we can multiply these together only when these two are the same. In other words, the number of columns of A equals the number of rows of B. Then it works. Otherwise, it's just not going to work. Let C and D be two matrices. Does C plus D squared equal C squared plus 2CD plus D squared? Well, not necessarily. When you multiply this out using FOIL, you end up with C squared plus CD plus DC plus D squared. Now, this is going to equal C squared plus 2CD plus D squared only if CD plus 2D plus DC equals 2CD. In other words, which means that CD equals DC. In general, it's not true, because matrix multiplication is not commutative. What would we call this matrix? Well, that's the zero matrix. We represent it with that symbol. Let I equal 1, 0, 0, 1, A equal 1, 2, 3, 4. Find IA. Works out that 1, 0, 0, 1 times 1, 2, 3, 4 is just 1, 2, 3, 4. In other words, A. In fact, it will always work out that way. I, 1, 0, 0, 1, is the 2 by 2 identity matrix. Sometimes, if it's ambiguous, we'll designate that as I2. It's the 2 by 2 identity matrix. IA equals A for any 2 by 2 matrix A. AI equals A as well. And in the same way, I3, 1, 0, 0, 0, 1, 0, 0, 0, 1, is the 3 by 3 identity matrix. IA equals A for any 3 by 3 matrix A, and AI equals A as well. Here's some properties of matrix addition. We talked about that earlier. Let A, B, and C be matrices with the same dimension. Let R and S be scalars. This one means that matrix addition is commutative. It's distributive. You've got a 0 matrix. You add that to anything, you just get back A. You multiply A plus B by a scalar. It's the same as multiplying each of those by a scalar and then adding. Okay, R plus S times A is RA plus SA, and R times SA is RS times A. Similarly, we have properties of matrix multiplication. Let A be an m by n matrix, and let B and C be matrices such that the sums or products below are defined, and let R be a scalar. Okay, matrix multiplication is associative. Okay, it's got these distributive properties. You can factor out the R. R times AB is RA times B, which is A times RB. If A is an m by n matrix, you can multiply it on the left by the m by m identity matrix I sub m and get A. Or you can multiply it on the right by I sub n, the n by n identity matrix, and get A. Oh man, matrix multiplication has some quirks. Cancellation laws are not necessarily valid. AB equals AC does not imply that B equals C. AB equals 0 does not imply that either A equals 0 or B equals 0. Strange stuff. Powers of matrix, you could probably figure this out. Let A be an m by n matrix. A to the k is just A times A times A times A, k times. The transpose of a matrix A is the matrix we obtain when we interchange the rows of A and the columns of A. We denote this by this symbol. Caution, it's ambiguous. This is not A raised to the power t. It's A transpose. Let A equal 1, 2, 3, 4. Find A transpose. Well, what we do is interchange the rows and the columns. So this is the first row. This is the second row. They become the first column and the second column of A transpose. In the same way, if B equals 1, 2, 3, 4, 5, 6, B transpose is going to look like this. Okay, the first column is going to be 1, 2, 3, and the second column is going to be 4, 5, 6. Here's some transpose rules. The transpose of A transpose is just A. A plus B transpose is A transpose plus B transpose. You can factor out K. Ka transpose is the same thing as K times A transpose. AB transpose is the same thing as B transpose A transpose. And A transpose inverse is the same as A inverse transpose.